So our paper is called Asking the Right Question, Exploiting Hidden Interaction in a Generative Framework for Multilingual Multitask Classification. I'm Sebastian-Antonio Toma, and together with my co-authors Camelia, Lemnaru, Vlad, Andrei, Negru, and Rodica, Potolea, I'm going to present the paper, and we are from the Computer Science Department of the Technical University of Cluj-Napoca. Okay, can you see the next slide?
Yes.
Okay. So yeah, the paper is in natural language processing. We focus on multilingual and multitask classifications, and we do this by using additional training data as instructional prompts or questions, as I'm going to further refer to them. And we use for that a generative language model. The challenges that we aim to solve is the model size. So we want a method for like small models, not large language models. Also, the limited availability of available data. So it's to gather more data. Also, in the case of imbalanced dataset, I will show you about this later. And yeah, also to try to solve the problem on low performance on underrepresented languages. The main objective is to improve the generalization power of such a multitask classification model, and other objectives that we aim to solve during this paper is to investigate the impact of prompt engineering in learning hidden interactions between tasks, also to measure the benefits of joint learning, and select the most informative additional tasks and annotations as our questions, so the most helpful ones. And at the end, we also study whether the model size and endowment pretending affect the performance or not. Okay, the data that we use for this is composed of online multilingual recipes, around 52,000 cookie recipes that are scraped from recipe websites, and they are in 6 languages. 2 overrepresented, as you can see, German and English, and the other 4 are underrepresented, like Dutch, French, Italian, and Swedish. The labels for the classification that we use are 3. So the first one is called mid-centric, so whether the dish is mid-centric or not. So it's a binary text label. And the other 2 are numeric labels. So it's the surface aspect level and the hydration level of the dish. Okay, some related work, as we can see it before, usually it's you have some text, you preprocess it, then you give it to traditional methods or deep learning methods, and then you evaluate it based on the label. For that, we use D5, which is a well-known transformer that acts with a pre-trained fine-tune and predict paradigm. Also, we also use the pre-trained prompt and predict paradigm, which is basically the prompt replace sometimes the fine-tuning step is just to trigger the downstream task instead of training again on downstream tasks. Okay, also these are applied in a paper that uses BERT to classify recipes based on similar labels like us. And they also deduced that joint learning is better for all of the classification tasks. And last but most important, in this paper, they don't do classification; they do intent detection and slot filling, and they inspired us a lot in this paper. So basically, what I do here, I'm going to summarize very fast. They just use the labels and they make a kind of questions like what we want to do of those labels. And I'll come later where our approach is different from this one. So in our proposed solution, we use MT5. We need MT5 because we are working with multiple languages. So we use a multilingual model to solve basically the same classification problem as this one. And first, we imply also joint learning. So before the baseline model, I think you can see my mouse. We give a prompt and append it to the recipe title and instruction to 3 MT5 models, and everyone is targeted to predict one of the tasks. So, for example, the dehydration level is 1, 2, 3, or so and so on. And then the first step in our incremental approach is to learn to train the model jointly. So now it's just one model for all the 3 problems. And this way we assume that, for example, the hydration level is the hardest one on the baseline model, so has the lowest accuracy. So we predict this one as the last one, so it can also benefit from the other 2. from the other two labels. So it will the model will try to predict the mid-centric, then the surface level, and then it will have that information available also for the iteration label. First we simplify the output, so it will be easier for the model, and also the prompt language and that we used and the connections and everything is in English. So the data set is multilingual, but the prompt language is static all over across the languages. So it's just English because it's the better performance language. Okay, now we used an additional fine-tuning task that we prepended to this task, sorry. So in this way, we didn't care about the performance on this task. We just prepended it. So the model, so the other three will benefit from it. And the task is basically predicting the oven settings task, which is equivalent with the triplet of temperature setting in Celsius or Fahrenheit degrees, with the time setting in minutes and the cooking program. This is more like an extraction task rather than a classification because it's not really classification. The model is basically tasked to extract those things, and after that he predicts the classification tasks that we need. Some recipes had and or because there are multiple alternatives in the recipes, or the model that we used to extract was not sure if it's that temperature or the other temperature. So that's why we have and or. In order to simplify things, we left just a maximum of 5 conjunctions, and from the disjunction we solved all of them. So we removed basically all ors, and we kept the complete value. So if we have A or B and A had some neutral or incomplete value, then we kept B. And if they were the same, so both have incomplete value or both were complete, then we keep the first one, basically like in a normal disjunction. Okay, now I'm going to actually the main contribution of our paper, which is the question-driven generative framework that, as I said before, was inspired from Eugen. But the difference is we do not use the labels to extract new questions, so we just use some additional data, redundant data that is available only during training, and you use those data to build this framework to fine-tune the model. So the model would better help we know like what to look in for our classification tasks. So this is it's a fine-tuned in a multitask manner. We have a variable number of tasks because the data is very sparse annotated, so the questions are not available for every entry in the data. And all the questions, options, and explanations were extracted by us from the additional data that is available during training. And basically, this is what it look like input. So a recipe, the title, and instruction as before, plus we give a question if it's available, and we also give options and explanations. So options, if it's a classification task, we gave all the labels. So we did this in order to further avoid some hallucinations that the model that can have. So to ground him to know which way to choose from. And the framework will look like this. So this is the input as before, the recipe title and instructions. Then we have some selected questions, and we also give the model the options, and with the gray text is some explanations for the options where they are available. Also, not all of the questions have options and explanations. Some of them is just, some of them are more like extraction tasks. And last but not least, the actual classification task, the one that we are interested in. And the questions with gray are only used during training, during fine-tuning, because the data is not available during testing. And the questions with green is the one that we use both during fine-tuning and during testing, and is the problem that interests us, the one with mid-centric, surface level, and the hydration level. Okay, as an example to how to instantiate QDGF, I show here how to instantiate it using the oven settings on the additional task that I talked before. So we transform also the temperature, the time, and the cooking program task in questions. We also give the model options, and so on. And also we use this just for fine tuning. And then at the end we have all our tasks that interest us in a joint learning manner that we also use during tests to test the model. Okay, so we have multiple types of questions. So we did an ablation study on how to select the best subset of questions. Every recipe has like maximum six questions that are answered, but in total there are like 14 types of questions, plus the one that we got from extending the triplet with time and cookie program, and whether the recipe is a multi-step or not, if it has and or not, if it's just one triplet or multiple triplets. So in total we have 18 types of questions. So this gives us to the power of 18 possibilities to instantiate QDGF. And yeah, the number of questions used between every experiment are 6 and 10, but it doesn't narrow down a lot. So we still have a lot of possibilities. So in order to choose the best questions, let's say, we looked which one are the highly correlated one with the problems. And yeah, we found the most correlated question to each problem. And we found that, for example, for the surface level, if we discard the higher correlated question, then the performance will drop significantly. So this is a mark for us that we should keep these questions in the final evaluation. We also did some specialization pre-training. So the T5 model that we used was pre-trained
We
by...
need to wrap it up, sorry.
Yeah, I will be fast. So we used span mask language modeling on top of that to further specialize it in the cooking domain. We also did some renaming for the labels, because for the other labels, there are numeric labels. So we found and give them actual text names. Okay, so now I'll go to the results. We assessed the we used to find in the model only in German and English, because yeah, we have more data out this. And for the underrepresented languages, we evaluated them in a 0-shot or a few-shot manner. So we can see that most of the models we obtain high informers for QDGF, the pre-trained one, or pretty consolidated in a joint manner. The image-centric was already pretty big for the baseline, but we still got the approval. But the biggest approval is especially for the hydration level that was pretty small before. And yeah, also other big improvements we obtained in the underrepresented languages like French and Swedish. And we obtained huge improvements, especially in the surface level 1, and especially in the 0-shot scenario using the QDGF approach. Okay, and also in the F1 score, we also obtained, like we see that the data set was highly imbalanced. We went from an F1 score for 36 to 77, and here is the biggest improvement. Like we see that the first class was not at all predicted in the baseline model, so the F1 score was 0, but with QDGF, we managed to arrive at 94 F1 score for the first class, which is the most underrepresented class. Okay, we also did a small study. I just want to highlight here that our goal was not to compare between base and large, but just to compare the improvement on base and improvement separately on large. And as we concluded in the paper, we cannot do, due to truncation, we cannot compare between base and large, but that was not our goal to begin with. And yeah, here I reported the maximum number of tokens used and the truncation that needed to do on large. And yeah, so in conclusion, we managed to improve the generalization power of our model. And yeah, here I just go again to the objectives and how we achieve them. And yeah, yeah, I think that's all. Yeah, and further development, just to another research paper to study actually the truncation, which is the optimal truncation, bias, and also considering other models or tokenizers to test how our framework could improve also them. Okay, thank you.